In the previous video, we have seen how to implement a brute force recursive approach in Java. And now what we'll see is how to improve a little bit the efficiency of this code by using memory caching and avoid recompute states in which that you have already met before. And so here the goal is really to avoid recomputing stuff that you have already computed in the past, so that we can shift a little bit the exponential to the right to be able to tackle larger problems. This is a technique that we call dynamic programming. So if you remember, the brute force approach was exploring a search tree like this one, okay? And of course here you see that I have decided not to represent the nodes that would violate the capacity. So if you would take, for instance, the item 3, you have only one capacity left here. The item 3 is requiring 6 amount of memory. You cannot put it, of course, there. And this is why I do not expand the search tree further in that direction. And again, here what you see is the capacity that is left after each of the decision. And here you've got the index, okay, while I'm progressing in the search tree. So each layer in the search tree represents a specific decisions for each item. Either you take it or you don't take it. Interestingly, what you can see in this search tree is that for some of the states, for some of the nodes that I have represented here with the same color, I have exactly the same capacity left, okay? So in this layer, here in the layer 2, you see that here, after having selected the first item and the second item, I'm left with a capacity of 6. This capacity of 6 comes from 11 minus 2 minus 3, okay? The same here, I'm also left with a capacity 6 because I decided to skip the first 2 items, but I have included here, I have included the item 2, which is this one. So I do 11 minus 5, which is also a situation in which you have a capacity left of 6. Okay? And then the sub-problem that you have to deal with here is to optimize the decisions for the items 3 and 4, knowing that you have a capacity of 6. Okay? So I hope that you are convinced that these are exactly the same sub-problem that you need to solve. And so the idea would be to avoid exploring this part. I will put it in red. Don't explore it. And you will simply here merge this and go into this state instead. And so if you do that, you will really reduce the size of the search tree. Okay, and it's not a tree anymore anyway, it becomes a directed acyclic graph because you will go sometimes in a node, okay, that you have only visited before. And you see that it's a directed acyclic graph because I'm represented here. Down is the direction, but you see that there is a kind of cycle here. Okay, this is why it's called a DAG, directed acyclic graph. So the goal is to do that dynamically, of course. Okay, we will do that dynamically, and doing so, we will reduce the exploration of the number of nodes that we will explore. The very classical way of doing that is using table implementation in dynamic programming. Okay, so let's see how we would do that using an implementation, using a table. So we will design a table in which you will put here all the possible capacities. So you've got the capacities up to 11. Okay, so this is capacity C. And here you will consider the items. Okay. The base case, if you remember, is that if you don't have any items, you know that whatever the capacity, whatever is the value of k, you know that you will have an objective function of 0. Okay. Then you consider the first item. Here, it has a value of 1 and it's requiring a capacity of 2. And so for k equals 0 and 1, here you cannot select it. I will use this. Here you cannot select it. But as soon as you arrive to a capacity of 2, you can select it. And therefore you can add this specific value. The benefits of selecting it is 1 up to the n. Okay. Then you consider the next item, which is the item the item 2. The item 2 is requiring a capacity of 3. It has a value of 6. Again, if k is equal to 2, you can only select the previous one. But here, when you arrive to 3, now you can select this one, and it has a value of 6. Okay? Then at k equal 4, it's the same, but when you arrive to k equal to 7, that becomes really interesting, because now you can select the two of them. And so if you add the two values, you've got 1 plus 6, 7 here. Okay? Where does it come from? It comes from here. Okay? You simply shift by 2. Sorry, you simply shift by 3, which is the weight here. Okay? You simply shift, you visit in the previous column 3 cells up, and this is the value that you will add, and you've got 7 now. Okay. The same for the third item here. It becomes really interesting here. Okay, when you arrive to capacity 5, you can take this item, which means 18 as an objective function. Okay, and you continue like that, and so here you arrived at 19, and you will take the 19 is adding up the 18, but you've got capacity of 7, so 5 plus this one that you can now take is 1, and so 19. Okay, and the result here is taking the third item and the first one, you've got 19. When you arrive to 8 here, you can select this one and this one. This is why you've got 24. Okay, what is important to realize is that the computation to fill in any entry in the table, you can do it in constant time, right? You always take the maximum between not selecting this item, which means taking the previous cell, okay, and taking this one minus the one that you will visit in the column before, but you just remove the capacity of the item that you just have included, right? And this is how you do it. And so you can really compute every cell in constant time. You continue like this until the end, okay, which is there. And then the best value is 40, is the one that you get here, okay? And then if you want to retrieve all the item that you have selected to reach this best objective function, you can simply follow the arrows, okay? You can simply remember where you are coming from in the computation, okay? Either you are coming from the previous one, which means that you didn't select this one, or you come from there, okay, by taking the maximum. And in that case, it means that you are selecting the current item. If you've got something that is like this, in that direction, which is oblique, it means that you have selected it. Okay, this is the optimal value. So what is the time complexity for building this table and computing the table? This is a question that we will answer now. But before that, let's look into the code of this implementation. So I will open my editor, which is here. And you've got the implementation in knapsack table, okay, here. What you can see is that this table is represented here as a two-dimensional array in Java. And I will initialize this table up to k plus 1 because I want to be able to index at capacity k, at capacity c, and so therefore I need plus 1 in the size of the array, and horizontally I've got the number of items. What I'm doing here is that I'm computing the first column in my table. If you remember, this was the first vertical column in my table, okay? I'm doing here, this is the base case. And then you've got here all the other columns of the table. So I will iterate over all the columns of the table. I will complete them one by one, okay? So the first thing that I'm doing here is for k equals 0 up to the weight of the current item, okay? Up to the weight of the current item. Here I don't have the choice, right? Because I go up to the weight of the current item. I can only select the one from the cell horizontally just before, okay? Because I don't have the space to do something better than this. Okay, then I continue here. I increase a little bit further the capacity. Okay, I'm going down in my column, and here I've got two possibilities. I've got the possibility of not selecting the item, so it means I'm just visiting horizontally the column, the cell before, and here I'm selecting the item. And so to select the item, I take the one following the pointer at k minus the weight of the current item that I'm adding. So this was the diagonal arrow plus the current value of the item. Okay, and the value that I put inside the table is the maximum between the two values. Okay, and at the end, I select here the bottom right value inside the table, which is the optimal value for capacity K and all the items. Okay, we can already evaluate what are the benefits of doing this by just measuring the time that we need to solve this problem. So what I will use here is a large instance, right? I will use a large instance, which is this one. Okay, so instead of this very small instance, I will introduce this large instance, introduce a variable for the capacity here. Okay, and so this will be the large instance. Okay, the large instance. We can look into this large instance. Okay, this is one of the instances that you have to solve for your first assignment. It has 50 items and it has a capacity of 5,000. And these are all the weights and values of the items. Okay. If I'm using my naive approach, unfortunately, if I run this, I run it. Okay. So it's computing here. You see that I can wait minutes, I can wait hours, and it's not returning, right? It's already out of reach for a naive computation with 50 items. You've got 2 to the power of 50. That's already a very large number, and you have no hope to solve this problem. Okay. For the dynamic programming approach with the table implementation, let's see what we have. Okay, I run the same very large instance, well, medium instance with 50 items, and we will see how much time it takes to solve it. Okay, you see that it's returning quite easily. In less than 1 second, I've got the optimal objective function here. Okay. Let's go back to the slide and study a little bit the time complexity of this algorithm. Well, the time complexity of this algorithm, since I'm computing every cell in constant time, is simply the capacity, which is the vertical dimension of the table, times n, the number of items. Okay, so for the problem that we just solved, it means capacity was 5,000 times times 50 items, which is 5 times 5, okay, which is less than 1 million, okay, and this is why it takes less than 1 second to compute it, okay, and so this is the demonstration that using a simple caching technique, we have already shifted the exponential to the right? The question is C times N. Do you consider that it is a polynomial time complexity? And the answer is no, it's not polynomial, because if you remember your computational courses, in order to be polynomial, you should be polynomial in the input size. And what we mean by input size is the number of bits that you need to encode the input. Okay? And here, the number of bits that we need to encode the capacity is log of C, right? It's an integer number. We need logarithm base 2 of the absolute value of the capacity. And so C is the exponential of the size of the input, okay? Is 2 to the power of log C, you've got C, right? And so this is exponential in the input size with respect to C, not to N, but with respect to C. And in that case, we say that it's not polynomial, but we say that it's pseudo-polynomial, okay? And if for small values of the capacity, if you have instances with quite reasonably small values of capacity, you can consider that it's polynomial. But as soon as C becomes very large, it's not polynomial at all anymore, right? and so it can really become expensive. By the way, a trick that you can use as a first approximation, but of course you lose the optimality guarantee, it is that you can scale down all the items by a same factor, okay? So that you reduce the capacity. This is of course an approximation, but this is one way to scale up a little bit using dynamic programming and still retrieve pretty good solutions. And this is pretty interesting when you have large item weights and large capacities. And so let's come back to the weakly NP hard problem. We said that the problem is weakly NP hard if there is an algorithm to solve the problem whose running time is polynomial in the dimension of the problem and the magnitudes of the data that is involved. So we are exactly falling into this definition that you can find on Wikipedia. And the knapsack problem using dynamic programming is a pseudo polynomial time algorithm, or we can also say that it's weakly NP complete. Okay. For some problems, it's not the case. You don't even have this kind of property. If I take the traveling salesman problem, it's NP complete in the strong sense. It means that you cannot find a dynamic programming to solve it like this.